Welcome to part 2 of our video on inverse trig functions. We're going to go ahead and look at some inverse properties. And as we're thinking of these inverse properties, we're thinking about how inverse properties work, say, algebraically. If I was to apply a cube root to x cubed, they cancel each other out and I get x back. So I want to make sure that I'm doing these inverse properties similarly, but also conscious of the domain restrictions. So just to review those. So for both sine inverse and tan inverse, those are restricted from the negative y-axis to the positive y-axis. So negative pi halves to pi halves. For cosine inverse, it goes from x to x. So I'm restricting those from 0 to pi. So I want to make sure that whatever I get back is within those restrictions. Let's go ahead and do the sines and the tangents first, because all of those need to have a value that lies between the range negative pi halves and positive pi halves. So for the first one, I've got the arcsine of sine of pi fourths. Pi fourths lives within that range, so I'm good. Pi fourths lives right here. So I do live within the range, so I can just cross these out. They undo one another, and I get the angle back pi fourths. Let's go to the next sine, and that's part B. So sine inverse sine of pi. Pi lives over here. So pi is not within my range. As you're working on these, a really good thing to try, because these are supplementary for the most part, is to do pi minus whatever the angle is, and that's going to give you the output that you want. I really want the value over here. Both of these have a sine value of 0. So by using 0 as my angle instead, I end up with the right answer, the right output. So pi minus pi is equal to 0. We could also do the math on this guy, right? So we could do sine inverse and work the innermost parentheses first, sine of pi. The sine of pi is equal to 0. Sine inverse of 0 is equal to, 0 is equal to the angle 0. Let's do the next sine one. Let's see, I know we've got a couple tans, but let's do the next sine one. So for this next sine one, it's the last one in this group, arcsine sine of 2 pi thirds. 2 pi thirds is this guy right here, also not within my domain restrictions. But these are supplementary angles. So this right here is 2 pi thirds. This right here is pi thirds. So that angle pi thirds is going to have the same sine value. So we're going to go ahead and use that rule of thumb that I had up here above. So we're going to go ahead and take pi, and we're going to subtract 2 pi thirds. That would be 3 pi thirds, and we end up with pi thirds. So I'm really like reflecting it across my y-axis. That's really messy, but pi thirds is my answer there, so pi thirds. Let's go ahead and do our tangent angles. I'm going to do these in red just because everything's such a mess here. Arctan tangent of pi fourths. This needs to live within negative pi halves to pi halves. Pi fourths does. It's right there. So I can go ahead and just write this as pi fourths. The next one that I have is 5 pi fourths. 5 pi fourths lives right here. It is not within the range. But in this quadrant, everything is negative. So I'd have a negative over a negative, which means that all of my tangents would be positive. So I can go ahead and use the same rule of thumb that I'd used before, and I can do pi minus my angle to come up with the angle that I need. So for this one, let's write it over here. I can do pi minus 5 pi fourths. So that's going to be 4 pi fourths, which is going to give me negative pi fourths. It's not exactly what I need, because negative pi fourths would give me a negative angle. So instead, I just want the positive of that value. You can memorize these if you want. I don't know how helpful it is. I think the picture is probably better. If you reverse that, you get the right answer of pi fourths. But really, we want to be in quadrant 1 where everything is positive, and using some nice symmetry, we get pi fourths. So these take a little bit of thinking. They're not just super straightforward values. The only ones that I have left are cosines. So I'm going to go ahead and erase what I have here. If you're still writing, go ahead and write this down. If you can't erase this, and I don't really want you to erase all of this, draw yourself another unit circle. I'm erasing all of this to do the cosines. We've got that nice rule of thumb that we used for sine and tangent by doing pi minus the angle or the angle minus pi. Let's go ahead and do this now for our cosine inverse. Cosine inverse, these are restricted from x to x. So from 0 to pi. So as long as my angle's within 0 to pi, I am good to go. So for this first one, I've got 5 pi fourths. 5 pi fourths lives right here, and it is not within my range. But I want the same cosine value. My cosine value, look how it shares it right here. This is the cosine value that I'm looking for. So I just really want to reflect this about my x-axis. So instead of 5 pi fourths, I'm going to choose 3 pi fourths. 3 pi fourths. Erase. Okay, the next one is pi thirds. Pi thirds lives right here. And it is within my range, so I can just cross these guys off, and I end up with pi thirds back. So these inverse properties are only straightforward if theta is within the range. And as we worked through those, we saw that theta was within the range for A. Let's see, that one was not. It was within the range for D. It was within the range for E. And I think that was it. So otherwise, we had to go ahead and calculate those values. Yep, I think I got all of them. Think through, really, more than calculating. Think through. Okay, number 2. Number 2 is much simpler, really straightforward. This is how our inverse trig gets used in practice a lot. I want to figure out some angles. Say I've got a deck here and I have an angle there and I need to figure out how to cut that. And I can go ahead and measure these distances, which happen to be, for angle B, I've got my opposite length, 4, and my adjacent length, 7. So I know that tangent does that for me. So the tan of theta is opposite, so SOHCAHTOA over adjacent, which is going to be 4 over 7. So I want to apply a tan inverse. So theta is equal to tan inverse of 4/7. And I can go ahead and just grab my calculator. I want 2 decimal places. Tan inverse of 4/7. Now you might be asking yourself, well, that is like way too easy. What about like making sure it's within the range and all of that? I get 29.74 degrees, right? 29.74 degrees. Well, as I'm thinking through the restrictions for tan and sine, they go from negative pi halves to pi halves. That would be any angle between negative 90 degrees and 90 degrees. These are going to give me acute angles only. And I do have an acute angle there for angle B. Let's go ahead and do C now. C, this next one. B, it's not actually C. I want to find angle B, which is right here. And I am given an opposite length of 14. And I'm given the hypotenuse, so directly across from the 90-degree angle. So I'm given opposite and hypotenuse. That would be sine. So SOHCAHTOA. Sine theta is equal to opposite over hypotenuse, which is going to be 14 over 21. So I want to go ahead and do an arc sine here, or a sine inverse. So sine inverse of 14 over 21 is going to equal my angle B. And I'm okay to go ahead and not worry about the range because B is an acute angle. It's less than 90 degrees. Let's go ahead and do a sine inverse here. Let me move this over so I can see my work. So I want to go second sine inverse of 14 over 21. And I'm not going to bother to simplify that. The calculator will do what it needs to do to find that sine inverse value, that angle for me. And I get 41.81 degrees. So 41.81 degrees. And let me just make sure I've got the first one correct too, 29.74. Great. So the calculator is really helpful here. Okay, so next, I want to evaluate and I want to give an exact answer. So we're going to use the triangles here again. So we're going to be building our triangles and we're going to go ahead and start with what's inside our parentheses. I don't have inverse functions, so I can't cancel anything out. So I'm going to be working my way inside out. The first thing I want to do is to pull this out of a cosine inverse statement. So I'm going to write it instead as the cosine of theta is equal to the trig ratio 7/10. SOHCAHTOA, this is adjacent over hypotenuse. So if I draw myself a triangle, I put my angle there. Adjacent to my angle is going to be 7. Hypotenuse is going to be 10. What I want to do is to find the sine of this value. So we want the sine of cosine inverse, but cosine inverse is always an angle. So I really want the sine of this angle theta. Sine is SOHCAHTOA, opposite over hypotenuse. So I just need this opposite side here. Let's go ahead and solve for that. So I'm just going to use the Pythagorean theorem. 7 squared, Pythagorean theorem, here we go. 7 squared plus my opposite side squared is equal to 10 squared. So 49 plus opposite squared is equal to 100. If I subtract that, I get opposite is 100 minus 49 is 51. So I get a radical 51. Radical 51. Now I want to find the sine of that value. The sine of theta is SOHCAHTOA, opposite over hypotenuse. Opposite, I'm just really building this triangle, right? Opposite is radical 51, hypotenuse is 10. So we get radical 51 divided by 10. Radical 51 divided by 10. Let's do the same thing for the next problem. I am going to erase, so hopefully you have a little more paper to work with. If you're not done writing things down, go ahead and pause. I'm going to go ahead and erase this, and I'm going to do the same thing for this next one. I know that this inverse function inside here is an angle, so I'm really looking for the cosine of that angle as my answer. I'm going to start with the expression on the inside first. Sine inverse of 1/4 is equal to theta, but that's not a helpful form. Instead, I'm going to write this as sine of theta is equal to 1/4. Sine is opposite over hypotenuse. Let's go ahead and draw our triangle. I'm looking for angle theta. I have opposite side, which is 1. I've got the hypotenuse, which is 4, and I want to find that adjacent side. The adjacent side is going to find cosine for me, adjacent over hypotenuse. Pythagorean theorem, a squared plus 1 squared equals 4 squared. So A is 16 minus 1. So that's going to be 15, and we'll put that in a square root. So my triangle, let me redraw, it's kind of a mess. 1, 4, radical 15. This is theta. I need adjacent to find my cosine. Cosine is adjacent over hypotenuse. Adjacent is radical 15, hypotenuse is 4. So this is going to be radical 15 over 4. So in both of these, I am taking the information on the inside and I'm building my triangle. I use the Pythagorean theorem to find the missing side, and then I go on the outside and I figure out the last little piece, which was cosine there and sine there.